Good evening, BSKL Year 13s. I'm here to do the webinar. I can clearly see that at the present, I have got 0 viewers for the online webinar, which is a bit disappointing. I will endeavor to proceed anyway, and you guys can watch this back at a later date. If you have any questions, then you can come and speak to us one-to-one, but I will still continue to go through the paper. Okay, I'm going to start promptly. I think I'm going to start straight away. I'm going to try and make it as quick as possible. I know it's a long paper. I'd love to get it done in under an hour. We will see how we get on. Okay. All right, let's do share screen. And then follow up with this. Okay, so your paper. Now, this is a mixture of Unit 4 and 5 for Edexcel IAL. All the questions are on spec and from real papers. I do have the breakdown for each one of these in terms of which paper these came from, but I'm going to get cracking straight away. Okay, so question number 1. In which of the following compounds does iron have the highest oxidation number? I've got to make sure that my tablet is behaving itself, and I'm on set on draw so I can write on it and highlight things. So in the first one, the iron is in a +4 oxidation state. So I'm going to be trying to be as quick as possible. The next one, which is we've got K plus times 2, so +2. We have an iron, which is in a question mark, and we have oxygen, which is 2 minus times by 4. Sorry, already made an error straight away. So -2 times by 4, which gives me -8. So +2 minus 8, iron must be in a +6. So +6 for that one. I'm going to erase then the working out of each one of them. Next one, we've got sodium at +1 times by 4, so +4 in total. We then have iron sitting at an unknown, and we have thiocyanate. That's interesting, sodium thiocyanate, which is Fe, followed by cyanide, which each one of those is -1, so -6. So iron must therefore be in a +2. Next one, similar in nature to the last one, so we can actually speed this one up a little bit. So we can go +3 for sodium, -6, we must be in a see, making errors all over the place. Must be in a +3 for iron. So the highest one there being B. Next, for question number 2, which one? Now this one is this one is actually one of my favorite questions. So first one of real interest. I'm select in order for me to scroll up the page. It'll take me a while just to figure out how to write on my screen whilst doing this. So, I've got 2 people watching. Hello, say hi on the chat. Be nice. Hello, I don't know who this is. Can I say who you are? Okay, next question. So it says, which one of these is not a redox? So really nice, this one. I've got chromium in a +3, and same again, -8 +2. That's in a +6. And they're both, this is a lovely example. This is a reverse disproportionation. Isn't that nice? I like that one. Next, so we've got manganese in a +7. It's good old manganate, potassium permanganate. And we've got manganate changing from a +7. And that one is changing from +7 to, oh God, -8, going up to -3 +5. Is that right? If I take it up to a +5, that drops out as a -2. And this is -8. This is going to be +6. Is that +6? That is a +6. So that one has a change in oxidation state, so that's definitely going to be a redox. So redox can't be that one, can't be this one. Next one, we're going from a +6. It's not, I'm so very sorry, that is not potassium permanganate. Or not permanganate, because permanganate is MnO4 minus, and that's MnO4 2 minus. And again, going from a +6 to a +7, definitely redox. Last one, nice to see the last one finish up, being the fact that we have +7 going to, it's not, +7 going to, that's interesting. So we've got -6 going up to +1, so that must be in a +7. And sulfur's gone from a +6 to a +6. So that one there is your not redox. That one there is something different. People are probably going to wonder what's going on there. We've got proton transfer going on in this. Even more interesting is the fact that the manganese actually technically isn't actually doing anything. So it's an oxygen. That's a form of acid-base reaction. Next one, nice and easy, this one, so hopefully it'll speed up a little bit. So we've got copper going with, so they have flipped the more negative. There's our more negative. They flipped it over as normal. So we run Earl, which is right minus left. So we've got plus 8 minus 0.34 gives me plus 46.46. So C. Nice and easy running Earl there. Also, if you want to do it via the redox line, we've got plus 0.8 and then plus 0.34, and it's the difference between the two of them. Nice and easy. Next, this cell is set up with 2 metal iron half cells. The digital voltmeter reads 0. Given that the components in the cells are all including and working properly, what is the most likely explaining for the 0 reading on the voltmeter? The cell has been set up in the wrong way. They have just discounted that one in the question. The entropy of the system is 0. Now that's an interesting question, that, because if the entropy of the system equals 0, then it won't. Then the reaction itself should not be feasible. Although, because it should be negative. Oh, I've got Anan. Hola, Anan. Hola. Happy Chinese New Year. So the B's a question mark. Not entirely sure whether or not that's going to be a good answer. The activation energy of the reaction is high. Right. So cells. This is a common answer, D. I had to check the Marta scheme for that one because I went for it with a little bit of, I was like, well, could be most likely explanation, and it was D. The reaction is at equilibrium. They do this quite a lot in cell questions where they will say to you, when does the voltmeter become 0? And it's where the system is at equilibrium when the concentrations often level out. So it was D. Next one, what is the electronic configuration of an H iron 3+? So iron metal itself is this with that guy. And then as you iron 1+, you remove the last one, iron 2+, remove the last one, iron 3+, you lose that one. So it came out as top, nice and easy. That one should have been a straightforward one. Next, ammonia gas is formed in the combustion of biomass fuels and is a significant pollutant when it is released directly into the atmosphere. One method of removing ammonia involves its oxidation using titanium 4 oxide as a catalyst. The best explanation for titanium 4 oxide is that the titanium contains many active sites on which the reaction can occur. Well, it is a heterogeneous. But it's not going to be a good explanation. It's not going to be the best. The fact that something have active sites doesn't mean that it's going to be a catalyst for that reaction. So many active sites is definitely not a good answer, although potentially possible. Is readily oxidized to a higher oxidation state. That is incorrect. Titanium will not go above a +4. It only has 2 4s and 2 3d electrons, so it won't go higher. It is readily reduced, that it can do. It can go down to titanium 2+ and 3+, and then readily taken back up again. Has a partially filled? No. So the last one, C for number 6, nice and straightforward. Next, a transition metal ion M forms with a complex with a bidentate ligand. Oh, okay. So straight away we can go M, bidentate, bidentate, bidentate. We've seen these pictures before. The formula of the complex is MB3. Makes total sense. So the shape of the complex is most likely in right. It's a trap question. They're wanting you to drop you into trigonal planar, and of course it's not. It's octahedral because we have got 6 coordinate bonds being formed. We're going to be in, we're still going to be an octahedral complex. Next. Oh, I've got 3 people watching. Woo! It's going up. Next. Okay. Which of the following lists all types of bonds present in a crystalline sample of tetraamine copper 2 complex? That's interesting. Tetraamine. So they're saying there's no water there. Isn't that fascinating? By the way, it's a lie. They're just ignoring. We know this complex. Okay, if we even do tetraamine, as that name would suggest, which I don't agree with, by the way. But what's going to happen is this is going to be a standard octahedral complex. So we have got, and these are all coordinately bonded. That ion there is going to be 2+ because the copper is still a +2, and these are neutral ligands. And so we're then going to have a sulfate ion bound to the crystal as well. So we have got covalent within the ammonia molecules and the SO42 minus ion, plus dative covalent bonds between the ligand and the transition metal, and we have an ionic attraction between the positive and negative ions then as well. So it's A being the right answer. Great question. All of them are there. Next, compound X is dissolved in water. Sodium hydroxide solution and dilute aqueous ammonia were added to different samples. In both, a precipitate formed, which dissolved in excess reagent. Right. So, by the way, lots of you are going to argue this and go, hang on a minute, we haven't been taught about these redissolving complexes that we see. Aluminium and zinc are the key ones to know about. They like to ask about these two. So if you haven't, add it to things in terms of extra reading. But aluminium and zinc are your top answers. But copper is a 2+, will not redissolve on excess. Iron 2+, will not redissolve on excess. Magnesium 2, will not redissolve on excess. None of those will redissolve on excess. The only one that does is zinc. Some students often ask why. It's because it's the smallest of all the ions. It has the highest. Notice that they're all 2+s, but zinc is the smallest of all three of those, being the fact that it is last in the D block. And we know when you go from left to right, and my voice is going, I'm sorry, guys. As you move from left to right across the periodic table, the atoms and ions shrink because you increase the number of protons while remaining the same amount of shielding. So zinc is the smallest there, highest charge density. It will redissolve on excess. Next, hence why, by the way, why aluminium does as well. Aluminium is a +3 ion, so it's very small, redissolves on excess. This was one of my favorite questions, this, because God, it makes you work hard for this, folks. So they have done the expression that relates delta S system to the equilibrium constant is, God, I had to work hard for this. So we have got delta S for the system, which equals delta S. So, now there's more to this, isn't there? There is delta S total equals delta S system plus delta S surrounding. So then what we realize is if delta S system is that, then what we can therefore do, we can also know that delta S system system equals shrink, which is, sorry, this is why you've got to use these and practice using them. Delta S total is RLNK. That's true as well. Now, what that means is you can therefore it's gone crazy. Oh no, I've opened the keyboard up by accident. Oh, nightmare. Let's go back down. Sorry, guys. Sorry, I need continuity with this as well. Therefore, we can sub these two into here. So we can then go, therefore, delta S system plus delta S surroundings equals RLNK. Now I can move it across and get the system on its own, which is to minus delta S surroundings, and delta S surroundings is minus delta H over T. So if you then end up subbing that in, you now get, I'm going to cross that one out. So we get delta S system equals RLNK minus, which drops in there, I'm going to draw that in as yellow, minus all of this guy in a brackets minus delta H over T. Well, if you make the brackets vanish, then the negatives will, a minus and a minus become a plus. So genius. Oh my God, what an effort of a question. But I keep hitting the keyboard with my hand. I'm sorry, folks. I'll get better. And so that's going to become that. And it becomes A. What hard work that was. Really clever, though. Like genius. Next, sulfuryl chloride. decomposes in a first order reaction. The half-life for the reaction is 2,300 seconds. In an experiment, the initial concentration is 1. What is the concentration? Right, so 1. So look at the time. The time they're going to leave it for is twice that. So it's going to go through 2 half-lives. So we're going to have 1 is going to drop to 0.5, and then it's going to drop a second time. Nice and easy. C. Dead straightforward. Next. Which of the following is the correct order of decreasing entropy? Decreasing chaos. Decreasing chaos is increase in order. So we want to go for, you should never say the word that. This is decreasing chaos. So we want chaos going to ordered. So we're going from chaos. Ice is a solid. That's ordered. Eliminate those two immediately. Steam is correct. That is the most ordered, the most disordered. It's a gas. Then we're going to go from gas to water, and then it's C. Because we've gone from gas to liquid, getting more ordered, followed by ice as a solid, most ordered. And just a nice thing just to chuck out there, we also know that we can roughly, it's not always nice to have numbers in your head. Gases tend to be in the order of 200 joules per Kelvin per mole in terms of entropy. Liquids tend to be around the 90, 100 marks. Solids tend to be around the 40s. So we are losing chaos. So C is the right answer. Next, right, what is the value of entropy of surroundings at 25 degrees? Right, there's all this question was doing was, so do you know that that's our entropy change? Do you know the equation? Lob in your numbers and don't forget, A, entropy is in joules per Kelvin per mole. That's kilojoules, minus 92,200. All over. Don't forget to convert to Kelvin. We know it's joules per Kelvin per mole. So 25 plus 273 gives me 298. So that divided by 2, this is where my phone comes out. I really need to get myself a better, by the way, never, ever, ever use your phones as calculators. They are such garbage. It's always worthwhile making sure. So, right, let's run that through. So we have got, now people are going to be interested in noticing why it's going to be positive in terms of entropy. So let's go. Oh, and the reason being is, right, and I've made a mistake, haven't I? Because, right, guys, this is another, what they're doing is here, they're checking to see whether you know, oh, I've hit the keyboard button again, haven't I? They're checking to see that you know where these values are coming in. Because there's a minus there, and what students are going to think is they're going to think that that minus is that minus, and it's not. That minus is that minus. So this needs to be in a bracket with a minus outside it. Minus and a minus becomes a plus. So we get minus 2, 9. I'm not doing very well there. 9 minus 92200 divided by 298, and I get a value of minus 309.4, and everyone chooses B, and they're wrong because you now need to flip the sign because it's a minus brackets minus 309.4, so which I get is plus, and that's C. Clever question, love that. Next. The questions so far have been genius, by the way. I think they're really, really lovely. Next one, straight out of AS. This is not A2, straight out of AS. Just got to be able to draw your enthalpy of solution cycles. So you see this, and they go hydrations, lattice, you calculate the enthalpy of, and I've already drawn the cycle. So we've got calcium chloride solid, and it can go in 2 ways, one into aqueous and one into gas. So this one here is the end, that's delta H sol, and this one here is delta H lat. And these are our hydrations. So we can lob on our numbers. So we've got lattice. Oh, look, lattice energy. So that one there is, oh, what's interesting is that's going up. Notice, this is important. The value is negative, which means it's exothermic. So you must be forming bonds. That arrow must be going up. Minus 2258. Put on your hydrations. Yeah. So we go, calcium is minus 1650. Chloride is 2 times minus 364. That way equals that way. Final equation. So we now go, that one is going against me. So my question mark equals minus brackets minus 2, 2, 5, 8, close brackets, plus brackets minus 1650, plus brackets 2 times minus 364. And I get a value of minus 120. Gotta know your cycles, folks. Can't make this stuff up. Next, standard entropy, mole entropy are given below. Calculate the entropy of the system. Always nice, dead easy. These ones are the easy ones, folks. These are your 3 marks. Make sure you know them. So we've got spray. Delta S system is delta S products minus delta S reactants. Spray, SPR, or super. I actually prefer super. So we've got products. So all we have to do is we go this value for carbon dioxide times 2. That's there. Water as liquid is there times by 3. Add those together. Get a total of those. There are products. Next, 1 of those plus 3 of those. Add those together. Get our total for reactants. 1 minus the other. And you get minus 138. Just run it through, folks. Nice and easy. Next. Okay, what is the effect of the rising pressure on the reaction mixture and of the reaction on the rate of reaction, equilibrium, and the value of Kc? Well, guys, pressure, Kc, I don't think so. There's only one thing that can affect Kc, and that's temperature. We all know this. I mean, come on. So, Kc, no change. Just look for no change. So it has to either be A or C. Next, what's it going to do to the yield? Well, hang on a minute. I've got 1 mole here and, 1 mole here. I'm going to have no change on the yield. The answer is A. Moving on. Next. Right, this one is knowing what happens to Kc. This is just, guys, you've got to have played enough questions around with Kc. Kc just, I can give you millions of questions to do if you want to practice it, but there are some clever little tricks, and Chris' question is saying, do you know your tricks? So I've got delta. By the way, this was a bit of a trap because they gave you delta C. The delta H was number 1 was up here, and then delta H2 was down here. Like they're in separate questions. That's not half going to confuse people. People are going to be losing these. Like, where's delta H1? I'll find delta H1. It's part of the same question. Still in question number 5, just part B. So okay. So delta H1. Look what they've done. They've doubled the equation. Right, so if you double an equation, you're doubling, this is the heat output when 1 mole of hydrogen iodide decomposes to form hydrogen iodine. Well, that's a thermal decomposition. Of course, that's going to be +5. It's endothermic. Well, if I do 2 moles, I'm going to get double the heat output. So delta H2 is going to be 2 times delta H1. And that's the genius, because there is no times 2. There's delta H1 is half of delta H2. Clever that. What that means is we can now, first of all, it is either B or D. These ones are wrong because of those guys. So this now drops into our Kc. Now, do you know what? It's quite funny that, because I've just gone, oh, come on, guys, Kc is only affected by temperature. So lots of people here are going to pick. Oh, actually, you can't even pick it because they're saying that Kc changes no matter what for B and D. The answer is D. The reason being is if you double an equation or half an equation, you square root Kc. If you go the other direction, you square it. So this is the square root. So the answer there is D. It's a funny it's a funny Kc trick. If you ever double the equation, you do change the value of Kc. Even though, I mean, God, that's a completely separate lesson to play in the mathematics behind why it doesn't. But it is true. If you change the balancing of the equations, you will change Kc value. It's because they're to stoichiometric powers. That's why. Anyway, moving on. The first stage in the manufacture of nitric acid is the oxidation of ammonia. So ammonia will be oxidized to form, oh, that's interesting. The modern industrial plant reaction carried out at a pressure around about 3 atmospheres. which is the following statement. Which of the following statements is incorrect? I hate these, find it really hard to wrap my brain around them. Even as a teacher who's well practiced, when they do the inverse, doesn't half freak me out. The raised pressure, right. So which one's incorrect? If I raise the pressure, it helps push reactants through the reactor. That is true. It's one of the reasons why you do raise it. If you just, what you have to imagine here is, if you have a system at pressure already and then go, oh, hang on, guys, we're going to raise the pressure. How are you going to do it? What you're going to do is you're just going to push the gas in at a higher pressure, and it'll push it through the reactor. So that is true. It'll shift the equilibrium to the right. Well, hang on a sec. I have got 9 molecules on this side, and I have got 10 molecules on that side. So if I raise the pressure, it will favor the side with fewer moles. So knowledge, moles, oppose. If I raise the pressure, the equilibrium will lower pressure by favoring the side with less gas, and it will shift it to the left. I'm done. There's my answer, B. Increased cost of reactor, of course it is. Increased energy costs. Guys, if you raise pressure, trying to keep it there, it's hard work, it's expensive, and the reactor must be at a much higher cost. You have to build it out of exotic materials. Just having a drink of water. Next. The platinum-rhodium alloy catalyst is used in the reaction. Which of the following is incorrect? The catalyst lowers the activation energy. Can I just point out, by the way, that itself is wrong. So if I was in an exam, I'd probably tick that box and go, I'm done, because that is not true. Nothing can lower an activation energy. It can provide an alternative route with a lower activation energy, but that statement there is wrong. But let's continue anyway, because I'm pretty sure I ticked it and then I had to go through and check. It has no effect on the equilibrium constant for the reaction. That is absolutely true. So that is a definite yes, because equilibriums increase the rate and forward reactions equally. It alters the enthalpy change of the reaction. That's incorrect. Now, people often wonder why for this, because if you... it's telling me that it alters it. This is wrong, because we know that what Hess said was any reaction that starts at the beginning and ends at the same place, no matter what route you take, it will have the same enthalpy change. Well, they've just said it alters it, and that's definitely not true. Oh, sorry, guys. My computer froze there for a minute, and I was like panicking. It crashed. So that's not true, and that is a definite not true. It reduces the energy cost of the parts of the process. No, if you add a catalyst, you don't change anything else in the setup. So the cost doesn't change. In fact, I mean, technically, you're having to buy a catalyst, even though you only buy it once, you still have to change stuff to make it fit. The operating temperature of this reaction is 900. The use of high temperature increases the rate of reaction and the Okay, so hang on a minute. I assume this is a continuing with the... I don't know, is it meant to be correct or wrong? Let's have a look. So, we're going to realize one of them is going to be different, don't we? That's what's going to happen here. So, increases the rate of reaction, the use of high temperature. Sure, that's very true. And the equilibrium yield. Higher temperature, equilibrium yield. Well, it's exothermic in the forward direction. So, this is going to fade. So, that's not true. That's not right. No. Next, increase the rate of and decrease the yield. That is true. Yes. Decrease the rate. Well, that's not true. And the equilibrium. Okay, so that one's no. And then decrease it. That's also a no. So the answer is going to be B, even though I don't really understand what the question is. They haven't used the word incorrect. They expect the right one. What a ridiculous thing to do. Thanks very much, EdXL, for that one. That's a garbage question. Let's continue. Sorry about that, guys. Got a bit of a cold. Okay, so we're on to section B. We're doing really well. We're 25 minutes on section B already. So we've just smashed through the multiple choice, by the way, in about 25 minutes, which is probably about right, really, for your exam-wise. I've probably gone a bit too long on each of them because I'm trying to explain each one of them. I hate the mark schemes, the way that they just say, oh, this is the right one, and that's it. It's nice to give a bit of explanation on the multiple choice, so I hope that's been helpful for you guys in year 13. Okay, you can see we're working out here. It's given our usual table. Give the order with respect to H2O2. So I found H2O2, there's my column, and I said, right, what's happened here? Right, they've doubled it here. I'm going to change that to a yellow highlighter. They've doubled it here, but this and this have stayed the same. So if you've doubled it, what's happened to the rate? It's doubled. So it's first order. First order, when concentration of H2O is doubled, rate doubles. Nice and easy. Next, what is the respect in terms of H+? Right, once again, find your column. There's my column. Where's it changed? Well, I could do reactions 2 and 3, but I decided not to, because if I do 1 and 2, if I do these two numbers, these guys have stayed the same. Makes it easy for me. So they've doubled it. What's happened to the rate from here to here? The answer is nothing. So 0 change. So 0 order with respect to H+ is when the concentration of H+ is doubled, there's no change to the rate. You move on. Nice and easy. Right, next, state the order with respect to iodides and explain with a reason. So this requires you to say the words direct. This is what, guys, just learn that word. This is directly proportional, a straight line through the origin. State the order with respect to I minus. This is a rate. This is rate against iodine. Anybody who has me as a teacher will realize that I like Steve against Sarah. And this is rate against iodide concentration, and it's directly proportional, so it's first order. Use the information to write the rate equation. We know that hydrogen peroxide was first. We know that iodide is 1. We know that H+ is going to vanish. So rate equals K, and stick them in their square brackets with no numbers. Nice and easy. Use the data from the table to answer the question and calculate the rate constant. Right. So first thing I've had to do, and notice I show my working. Yeah, I've reorganized my rate equation that I have just written above to make K reorganized to make K the subject of the formula. God, that took me ages, mathematicians. Sorry. So I reorganized to put K there, and then, guys, I chose a complete string of data. So what I now did was I just went, right, let's just take row number 1. Let's just take all of this data here and just slot these numbers in. So I was like, rate, whack that rate there. Next one. Hydrogen peroxide concentration, whack that in there. H+, don't need it. Iodide concentration, whack it in there. Run it through my calculator, and I got that. It was really straightforward. Just required you to have just know how to use the data. Dead easy. And don't forget your units. So just to do the units bit for anybody who wants to know, rate is moles per dm cubed per second, all over hydrogen peroxide, moles per dm cubed, times by iodine, moles per dm cubed. Right, cancel what cancels. That guy cancel with that guy. This guy now needs to come up. So you flip its sign. So moles to the -1, dm to the +3, and S remained exactly the same way it was. So there are my units. Just nice to run units. Next, one of the trickiest questions on the whole paper. The rate, so it's set, nitrogen dioxide reacts with carbon monoxide. I gave you an equation. The reaction is second order with respect to nitrogen dioxide and 0 order with respect to carbon monoxide. It then said, suggest a possible 2-step mechanism for this reaction. Write the rate determining step first. Right, this was tricky. So I kind of almost need to go back to like basics on how I went about this, because what that question tells me is the reaction is second order with respect to nitrogen dioxide, which means if I was going to write a rate equation, rate equals K, I'd have that to the power of 2. And 0 order with respect to carbon monoxide, which means it would just be that as my rate equation. Now, the way you always know a rate determining step is because you find the reactants in the same ratio as is found in the rate equation, which is the power of 2. So in order for me to know my rate determining step, I knew that there must be 2 going in, and for carbon monoxide to be completely missing. I couldn't have carbon monoxide here because it was 0. So it had to just be missing. So I then went, well, all right then, it just needs to be there. I'm just going to go to that. And went, what am I going to create? The answer is I didn't really care. I was just like, do you know what? I've got 2 of them going in. I don't care what I make because it's going to disappear anyway. I just need to have those 2 things form a single product. So I just said, let's make it become N2O4. I was just like, it doesn't matter what I create there. I've just got to have them go together. I could have had it, by the way, if you'd wanted, I could have had this happen. I could have done that, N2 plus O2. I could have had it and then balanced to make it correct, which would have been that. I could have done that. And then as long in the second step, I make everything vanish. But I didn't. I wanted to make it easy for myself. So I was like, stuff it. Let's just combine it. Let's just make it easy. Let's make one product that's bigger. Right, now that I've created something that I've never even heard of before, I now need to destroy it. Because this is not in here. There's nothing here. Now look what I've got. At the moment, I've got him going in. I get him from this first step. But then I have nothing else at all. So what I now need to do is I need to create an equation which will give me everybody else and make that vanish. Well, if I want that to vanish, they need to be on opposite sides. So put it back in. So I put this back in at the beginning and then said, now that I've put that back in, what else do I need? I need some carbon monoxide. I need some nitrogen monoxide and I need some CO2 over here. And I just put them in. And when I balanced it, guess what I got? I got my initial equation. This is one of the most tricky questions on this whole paper. And do you know what? The kind of the leaps of faith that you have to make for this, you've got to understand the rate determining step is linked to the rate equation and understand that that rate equation telling you that carbon monoxide's there cannot then appear in the rate determining step. And realizing that that too must be as the stoichiometric ratio in the equation, this has all got lots of neat little caveats that make this tricky. Really lovely question though. And I have a whole bunch of these questions if people would like some practice. So I'm happy for you to come and ask me for those and I'll drag them out from wherever folder I have them kept in my insane pen drive. I will find them all for you. Right, next. This one required you to use the data book. It tells you the pages. You just had to go there and find it. So it said, calculate the standard entropy change for the system. We're just running super again. We've already done super already on this paper. This is easy. We're thinking, yes. But this time, we just had to use the equation from above. And everything was in ones. So we found the products. I found the... Very quickly zoom out. I'm actually losing my voice. These, of course, are my product that I've taken from page 20. And these are my reactants that I've taken on page 27. I ran them through, did them bit by bit, and I get an entropy change of -13. Very interesting. By the way, this question, I like this question because from doing enough questions and over the years, this question is incomplete. There's a whole group of questions that usually follow that question. The first question that commonly comes up is, explain why the entropy change is so small. And you go, because I've got 2 moles of gas going in on the left and 2 moles of gas going in on the right. So the value is going to be tiny. This is 13 joules. Are you messing? That's a miniature amount of energy. I mean, heck, I sweat 13 joules. So that's nothing. So it has such a tiny change because we've got gases, 2 moles of gas going in and 2 moles of gas coming out. So it's a very common question to follow it up. The next thing is, how do you explain the fact that it's negative? This is saying that it's decreasing in chaos, decreasing in disorder. So could you explain it? And the reason why you'd probably explain that is because carbon dioxide is linear. So because carbon monoxide and nitrogen monoxide are very similar in size. So they're both single units so we've got carbon monoxide with a triple bond over there and nitrogen monoxide as well, something similar. And then we've got nitrogen dioxide, which funnily enough is bent and has a delocalized ring system, followed by carbon dioxide, which is linear. So this one has a slightly increased amount of chaos. It's a lovely question with like loads of great detail in it. Next. Okay, given that the enthalpy at 298 for the reaction between nitrogen and oxygen is this, calculate the standard enthalpy change for the surroundings, run it through. This is just another straightforward using your numbers. Notice my minus signs going in properly this time, there and there. Yes, it's going to become plus. And there's my times 1,000 because we all here, God, I wonder how many students forgot that that's in kilojoules per mole. And this one's in joules per Kelvin per mole. This one's in joules. It's such an easy conversion to miss, and everyone quotes 0.78758 instead of 758. So do watch out. Next. Calculate the total entropy change, total, for the reaction. Stay what's there. Entropy total equals system plus surroundings. I've got my data from the system. I've got my data from the surroundings from the previous questions. You can see my calculation, run it through, and then it says, state what the sign indicates about this reaction. Well, the entropy of the total entropy is positive. This means the reaction is very feasible. Nice and straightforward. They love this question. It's a really nice one. They like this. Comment on S total and its feasibilities. Time to do the whole of the rest of the thing in a voice like Alan Partridge. Hello. Next. To Yorkshire. Okay, write an expression. This question was hard work. So jumped straight into equilibrium. We've got a nice methanol, carbon monoxide, ethanoic acid. Said, write an expression with Kp. Nice and easy. This should have been well practiced by you all. Kp equals, by the way, tiny things to mention. Number one, you're not allowed to use square brackets. No, don't do it. They are circle. They are these. Yes, these are good. Yes. These are good brackets. These are bad brackets. The next thing, the P should follow it, not go in front. But it'd be interesting to know if they'd penalise you for that. I mean, the mark scheme didn't really say very much, but the P is meant to go after. And it's a lowercase p, by the way, not an uppercase. Do watch out. It depends how picky the marker is. But it was a nice, easy form. Calculate the partial pressures of methanol and carbon dioxide at the equilibrium. So, when I first saw this question, I had a terrible moment where I was like, oh no, it's going to be a quadratic. I'm going to get lost in quadratic maths. And then I was like, 50 in of both reactants. Same moles in, and they're in a 1-to-1 ratio. I was like, winner. This makes things a whole lot easier because these two are going to drop by exactly the same amount. And with the initial value being the same, their end value will be the same. So the total pressure, the equilibrium, reached at a pressure of 32 atmospheres. And it said that the partial pressure of the product was 2.2. So if I did one minus the other, I got the partial pressure for the leftover gases and then divided by 2 to get both. Thought that was a really lovely little question. Do you know what? When I first saw it, I freaked out thinking it was going to be a quadratic. I saw the marks and went, oh, this is going to be easy. So it gave me a big hint that I did check for it. Next, calculate the value for Kp at 175, include a unit in your answer. So I wrote my equation out again, then filled in my data. So the partial pressure of 22.2 for the ethanoic acid, 4.9 squared, because there's two of them, ran that through, put it through my calculator, and I got 0.925. And of course, my units are atmospheres to the -1. If anybody's not sure on the units, the reason for those units is because Kp is one thing at the top being atmospheres, and on the bottom, 2 ATM times ATM. Cancel what cancels? There's 1 ATM left, but it's on the bottom. To bring it up, you've got to flip its power. ATM to the -1. Nice and easy. Next. Good question, though. Next, equilibrium moles. Another sample of 50 moles of methanol and carbon monoxide allowed to reach equilibrium. The following temperature of 93.6% methanol was converted. Right, complete the table below. Okay, so 93% of methanol was converted. So take the 50 of methanol, divide that by 100 and times it by 93.6, and I get 46.8. So that was the amount I was going to make of this, and whatever's left of those two will be the same, 3.2. Next thing, calculate the partial pressure. Well, the partial pressure is mole fraction times by the total pressure. So the mole fraction is the moles divided. It's a fraction of the total moles. So it was that number there. And how many people then divided this by 50? They shouldn't, because it was 48 for that, 3.2 for that, and you had to add all of those together to get the total moles. So 46.8 over 53.2 gave me a mole fraction of 0.88. Times that by the total pressure, and I get 28.15 atmospheres. Great question. I have 4 people watching. Hola, everybody. Happy Chinese New Year. Next, is the reaction exothermic or endothermic? Explain why. Right, this question was really clever. Now, the first thing I did was when I saw the question, I went straight to the equilibrium. And I went, exothermic, instantaneously. Now, I wonder how many people would be able to tell me why I managed to do that so quickly. I looked at that and I went, I have 2 things combining to form what? That's making bonds. Mexobendo. Making bonds is exothermic. Breaking bonds is endothermic. Mexobendo. So this way, if I was going to smash that into those 2, that would be endo. And if I'm going to make it, it's going to be exo. Must be. So I knew the answer instantaneously. And I was like, what's the marks? Let's have a look at the marks and see what the value is. Because the problem is, got to be careful here. It was only 1 mark. But it does say that you must explain your answer. I did wonder about doing the making and breaking bonds bit, and said that the reverse was going to be a thermal decomposition and breaking of bonds, so it must be endothermic, so the forward reaction must be exo. I think they probably would have accepted it. But instead, I thought, you know what? I better do this properly, because I've been given 2 different temperatures. I was given one at a temperature of, first one was a temperature of 175, and I got a Kp of 0.925, and that had a moles of moles of products of 22.8. And then it said it is done at a lower temperature. And then I looked at my equation and I realized that I had a higher moles at equilibrium than I did in the first one. Now what that meant is, because I've got higher moles in the first one, I'm going to have a larger number on the top, a bottom note, so I've got more products. Partial pressure of ethanoic acid product has increased. Equilibrium has shifted to the right when the temperature was lowered. Forward reaction must be exothermic. And don't get me wrong, I have gone to town on that question to do that properly. For 1 mark, that could have been worth 4, but it wasn't. Clever though. Next. How, if at all, does the addition of methanol to the equilibrium mixture affect the following? The equilibrium constant, well, no changes. The only thing that affects Kc is temperature. Jargon. Next, the equilibrium yield of ethanoic acid. Well, the yield's going to increase. We know this because we know that if you increase the methanol, the equilibrium will shift to remove it. So I have to run coughs probably here. So I'm saying, number 1, the methanol is a reactant. So meth is a reactant. If I raise it, the equilibrium will lower it by favoring the forward reaction, shifting it, shift left to right, increase ethanoic. Yield increases, increase content of methanol. Methanol is a reactant, equilibrium shifts to reduce methanol. Shift left to right, ethanoic acid increases. Again, 1 mark. And I have gone to town, year 13, because I do not want to do a question, spend my time doing it, and lose a mark because I didn't say what they wanted me to say. So I'm going to do a nice, good routine answer. This is equilibrium. I'm running coughs, and I'm doing it properly. Because next time it'll be worth 2 or 3, and I'm going to smash all those marks because I'm so well practiced. In industry, catalysts are used even though they're often expensive. State and explain 1 benefit to the environment resulting. That was this question, bloody environment. You needed to actually say, well, hang on a minute, if we use a catalyst, that means we're going to have to heat it less because it reduces energy requirements because it provides an alternative route with a lower activation energy. So if there's lower energy, then I burn less fossil fuels to get the heat. which means I reduce the amount of CO2 being released into the atmosphere. But you cannot get that mark without mentioning fossil fuels need to be bought and fossil fuels need to be burned to generate heat. There is less energy required because catalysts lower them, so less CO2. They required a big, long answer. Be thorough. Less energy means less fossil fuels, means less CO2. Yeah, which means less global warming. Do you know what? I think I've lost a mark there. One benefit to the environment. Less global warming. Done. I'm adding it. Love that. Next. Oh, right. Guys, we're into colors. I have lost my page. My tablet's gone mad. We've got to colors. Whoa, I don't know why all of a sudden it's decided to be such a, oh, I've done something. Oh, I've done something badly. Oh, no. No, don't do this to me, computer. Uh-oh. My computer's having a bit of a hissy fit. Uh-oh. Oh, no. U13, my computer's having a little bit of a fit. I'm not entirely sure why. It's kind of frozen. Oh, no. Come on, computer, don't do this. Oh, yeah. Not sure what to do about this, folks. My computer has decided all of a sudden to take a little bit of a break. That's a nightmare. I'm kind of appreciated to come back to life, really. Oh, I'm not entirely sure. It's not like not. Oh, I'm trying to. There we go. Oh, right. I don't know quite what it's done. It still won't let me. It's still doing something funny here, but it's desperately trying to work. I don't know what I've clicked, but it has kind of semi-frozen. Just going to zoom it out so I can see the question. Okay, sorry about this, guys. Next. Okay, so this question asked us to identify from each of these substances, right? So the formula of the chromium-containing species. So from the chromium sulfate, we realize that the Cr is in Cr3+, so that's the species. The green, so we've taken that and we've added sodium hydroxide and formed a green precipitate. It's a +3 ion, which means we're going to have the chromium triaqua trihydroxy complex in brackets as a solid. There's my green precipitate. It then redissolved on excess and formed a green solution again. My computer, by the way, is still having a massive hissy fit. Next, so anyway, it redissolves to give the chromium hexahydroxy complex -3. Next one, my yellow solution, right. This is the clever one. Notice that the yellow then went to the dichromate. So we know that dichromate is orange, but chromate is yellow. So that's CO4 2-. It then asked us to balance the equation. Hydrogen peroxide going to two OH minuses and add your 2 electrons on the correct side. So relatively easy for that one. I think this is actually about to now not let me go any further. This could be a little bit of a nightmare. Not entirely sure how to solve this. Oh, I've done something, and I think it might. It's gone completely mad. Oh, it's gone really, really crazy. I don't know what this is thing. It's gone completely nuts. Oh dear, it's gone mad. Oh, it's letting me scroll. No, it's not. It's thinking about letting me scroll. Oh, come on. We were doing so well. We're doing so well on the paper. Don't do this to me, computer. Come on, come on. I don't know what it's doing. Those people who are on Macs right now are going, and that's why you don't buy a Windows computer. I honestly don't know what this thing is doing. I honestly don't know. I'm trying to figure out how to solve it. CPU is up there. I don't know what else is draining. I'm really hoping it's going to come back to normal, and it's so not. It's freaked. Eek. Oh no. It's really now massively freaked out again. Do you know what I might do? let's close. Let's see if I can close Microsoft Word. I think Microsoft Word is what's causing me the trouble. But then the problem is it's whether it's going to let me do that. And it's clearly not going to let me, is it? It's moving all the time. I don't like it. It's gone completely mad, this, folks. Oh, the problem is I can't do it without this. And that now won't disappear. I don't know what to do here, folks. I think I might end up having to... And the problem is I'm transmitting from... This laptop has gone completely stir-fry crazy. It really has. Oh, it's letting me do that now, which is really irritating. Oh, I think all of a sudden might, if I can scroll down, I think I might be back. I am. Oh, please do what I'm asking you to do, please, computer. Oh, I think I might be back if I can just, come on, please, behave. I'm so sorry, year 13. Steve Jobs is laughing in, yeah, thanks for that, Anam. Appreciate it. Lol. With that, I'm back. My computer has managed to resolve itself. Oh God, has it? I don't know if it has. Right. Okay. And the problem is now, you see, this is now becoming ridiculous. Come on, computer. Just do what I'm asking you to do, please. There we go. Reagent X. We want to turn the chromate yellow into dichromate. We know that there's an equilibrium there in terms of acid, which is then the next question. Write an ionic equation for the conversion to solution C, which is sodium dichromate. State symbols are not required. So dilute sulfuric acid provides us with these H pluses, pushes the equilibrium back this way, and it turns orange. So nice. Right, one of the trickiest questions on the entire exam this was, and it was a nightmare. Chromium also exists. Right, I'm sorry that it's taken so long to get it all back, guys, but I'm glad we have now. So, okay. And we're nearly at the end. We're not far off. So chromium also exists in a 2+ oxidation state. Use the data book to determine the feasibility of the disproportionation from 3 to 2 and 6. In your answer, show both half equations. Right. So what did I do? I said I want to turn chromium 3. I'm going to highlight this in different colors since I've used highlighter already. Chromium 3 into chromium 2. And notice I balanced the equation with 1 electron. I then said, but I also want to create chromium 3 into chromium 6 as the dichromate ion. Notice that the electrons were on opposite sides. And I was like, oh, that's interesting. Well, hang on a sec. If I'm going to do this via electrochemical cell data, I need them both written down as a reduction. So I then decided to reverse the second equation. And I wrote it as dichromate to chromium 3. So then I could compare their values directly. And I realized at that point, this isn't possible because now that I had the 2 equations and they were both written down as reductions, I could compare them. The rule is flip the more negative, and that's that guy. And if you flip that over, you notice that both chromium 3s are on the wrong side. The chromium 3 will end up over here, and the chromium 3 on this will be over there as well. What that means is this reaction will not be feasible. However, they're going to want me to explain it using e-values. So what I then said is, well, hang on a minute. Let's just write down the equation. Let's combine the equations as if it did happen. So I then flipped the other guy, and since I had already done it anyway, I just combined, you'll laugh at this, I then combined this guy and this guy. And when I combined those, I got the equation that they were asking me to do and asking me to see if it was actually possible. And then I ran Earl as normal, and I knew it was going to give me a negative EMF, which means the reaction is not feasible. That's hard. That's A2. That's epic. It's really tough, that. That was really, really hard. Everything I've done, I've given them the overall equation. I've given them the E value being the EMF being negative. I've shown Earl in the top. I've shown both half equations, both forwards and backwards. You know, I've shown everything they need to gain. I gain every mark, but that's tough, that. And I know students would look at that thinking, oh my God, that is beyond me. I think my computer may have frozen temporarily again. Oh dear, come on. Hoping we come back now. There we go, it's back. Next, okay. Question number 14, even though it's not 14. Right, more colors. So, copper sulfate, it says identify A. So we're going to take an aqueous solution. We're going to take an aqueous solution. So that's copper hexaaqua, and I'm going to add sodium hydroxide. We're going to get my tetraaqua dihydroxy complex as a solid. Then we're going to heat that solid and it turns black. What black solids do I know which have copper in it? That's going to be copper oxide. They've heated it until it's thermally decomposed. Next, he takes A and he adds dilute ammonia and forms a dark blue solution. There's my tetraamine diaqua copper 2 complex. Next one. Then I take copper iodide and I add sulfuric acid. That's copper 1, guys. That's important. Copper 1 oxide is really rare. It's also white. And I heat, they've added sulfuric acid, and I formed a pink solid, and there's only one pink solid that I can see in that diagram, and that's copper metal. So I've formed copper metal. And the solution, of course, is going to be copper sulfate. And then they've asked for a colorless solution, F. That one was the trickiest one there. So what I've done is I've given the dark blue that I knew it was going to go to upon shaking. I've given that guy again. But this time, I've put it as a +1. Because remember, in order to be a color in transition metals, you need an incomplete D subshell. And copper 1 is full. It's colorless. So any copper complex with ammonia in it would have got you that mark as long as it was +1. Next, identify the reagent or formula used to convert B into copper sulfate. Well, you're going to add sulfuric acid again. Just add dilute sulfuric acid. You have to heat that, by the way. You can't just do that. Give a full to add it. It doesn't do it. It will actually go blue a little bit. It will. But you need to heat that. C and F. This question, this one made me think, because I was like, hang on, C and F. C and F. What's special about C and F? Because C and F, well, F's a complex, C's a complex, but A's a complex, and okay, B's not, B's an ionic solid, but like E's a complex, and like the what? And I went for, I took a stab because I was like, that's a stupid question, but the answer was complex ions on the mark scheme. I was like, that's a trick question. Now, why C and F? I don't know. Right, next. We're nearly there, folks. Give the formula of manganese 4 oxide. This is straight out of GCSE. Mn 4 plus, O 2 minus. Cross them down. MnO2. How do catalysts speed up reactions? They provide an alternative reaction pathway with a lower activation energy, so there are more successful collisions. You've got to give it. You've got to give all of it, folks. Every single one. Give that whole thing. That is how a catalyst works. Even you do, because that's 2 marks at A level, you need more successful collisions. You need it. Whole thing. Explain how transition metals can act as homogeneous catalysts. Right, well, the homogeneous catalysts we know move up and down in oxidation numbers. So transition metals can form multiple oxidation states and can accept and donate electrons easily. Nice and straightforward. Next, if it's going to let it move. Next, suggest why the preparation of equation 1 may described as a reverse disproportionation by considering the relevant oxidation states. MnO2, manganese is in a +4. In MnO4 minus, Mn is in a +7. So I've just got the first mark just for stating all the people in it. MnO2 is oxidized into MnO4 2 minus, manganese +6, and MnO4 minus is reduced from +7 to +6. And they're forming a single species. reverse disproportionation. Just quote all the numbers and say what both are doing. Probably should be saying the fact that they're forming the same product, really. If I was gonna, I'd be looking at, I'd probably lose a mark there, I reckon. I'd want to actually say, and these two both form the same product. Wait, well, won't they? Next, come on, computer. This computer is really struggling today, and I don't know why. It just is, and I just can't really figure out what's going on here. Next, it's really struggling. It's because the paper's so massive and there's drawings everywhere. It's just not liking it very much. Next, explain by reference to these half equations why increasing the concentration of hydroxide ions alters the electrode potential to make the preparation ions more likely. It's not just more likely, it's to make it possible. Because guys, if you look at the top equations, they want the two half equations combined to form equation 1. And what they're actually wanting you to do is, if you flip the more negative, which is that guy, you flip the more negative, then you don't make what they want, which is a problem. You're trying to make MnO4 2 minus ions, the manganate 6 ions. You're trying to make him. And what's happening is if you reverse them, if you flip them more negative, that guy ends up over there, and what you're going to make is him and him in a disproportionation. What that means is the initial reaction is not feasible. However, if you increase the concentration of him, what's going to happen is the equilibrium of equation number 2 will push it that way. And you're going to increase, I need to get this right here. It's what's going to do is you're going to then shift it to the left, making it more negative, because you're shifting it to the side, which is gaining electrons. So you're actually going to make that equation more negative. You're adding more negative species. You've got 4 of them on that side. That's the negative side. That's the positive side. Only 2 negatives. You're increasing its negativity. If you add in shed loads of minuses, it's going to attract electrons. Hang on a second. It's going to repel electrons and push it that way. So you make that more negative, making the reaction more feasible, because the E cell will become more positive. You're pushing that equation from right to left, and therefore you're going to make it more negative. It's clever, that. Next, identify the gas formed. So that came from the equation in number 1. When you actually scroll up, see, the problem is, you see, it's trying to add all my writing to this. If I save this, is that going to help me? Maybe that wasn't the best thing for me to do anyway. I've just saved all my extra writing, and now it's really freaked out. Oh, there we go. Go back to the original equation. It tells you I'm making oxygen gas. So that tells me, oh, look at that little circle. It's just going to stay there. Goodbye. So we're going to make oxygen gas. It tells me that. It's really, really struggling now. I really don't know why. Right, so go back to here. Going to make oxygen gas by appropriately combining these 2 equations, write the ionic equation. If you combine the 2 equations, there's your overall. Everything cancels right down. All the OH minuses disappear. It's dead straightforward. Happy to walk you through that, guys, if you need to. Identify the main hazard. The main hazard is sodium hydroxide. Sodium hydroxide, guys, is crazy corrosive. Proper dangerous. Caustic is lethal. So wear goggles and gloves. Gloves being the top answer, though, considering how many times I've burnt myself. Identify the reagent that would use to make manganese 2 hydroxide from manganese 3 ions. All right, this was a clever question, because I was like, well, hang on a minute. I've got manganese. The reagents to use to make manganese 2 hydroxide for the preparation of manganese 3. Hang on a second. So what they're saying here is make him. And I was like, okay, well, what I need a manganese 2 containing solution, because reagents, I'm going to choose the nitrate. I always choose the nitrate because nitrates are always soluble. And then I'm going to follow it, and I'm going to add to it sodium hydroxide to turn it in to manganese 2 hydroxide precipitate. And we're done. Next. Oh, this thing is really strong. Next, draw a dot and cross diagram for the cyanide ion. Nice triple bond in the middle. The bit that's going to trip everyone up is him. The problem is the cyanide ion is a negative ion, and you have to recognize that usually it's KCN or sodium cyanide. The K, this is ionic. The K, which had one electron in its outer shell, gives it to the carbon atom over here to form the Cn minus, and the carbon is the one with the negative charge. So clever question, looking to see how many people knew that. Explain how cyanide ions act as a ligand. The carbon atom in the cyanide ion can donate a pair of electrons to a transition metal ion, forming a dative covalent bond. Suggest the name of the shape, and that's octahedral. And that, year 13, is how you do paper. It's how you do your mock paper. So what's amazing is I started at 7, it's 8:05. We have smashed through this year 13. I am really, really pleased. Stop sharing the screen. Is it going to bring me back? It is. It's late. It's been a long day. Year 13, I hope it's been really, really helpful. If you have any further questions, please don't hesitate to come and ask me, Miss Childs, or Miss Allday. We are always here to help. But I hope it was helpful. Mainly, it's nice to actually go through some of those multiple choices, because in reality, the multiple choice mark schemes are usually terrible. It just gives you a yes or no. So I hope that was useful. And if you have any further questions on the other ones that we've done, just come and see me, and I'll always give you the time. I hope you have a lovely. I hope you've all had a really nice, lovely Chinese New Year, and continue having a nice holiday. I'll see you tomorrow for Unit 6. See you later, guys.